Hello, ladies and gentlemen, and welcome back. Root Beer here, looking at the very last question, question number 10 on our 2016 Euclid paper. So we're going to finish off the contest in this video. If you haven't taken a look at question number 10, now is a great time to pause the video and see how far you can get. You probably should be able to get at least A, maybe B. C should probably be a challenge. That's just usually how it goes. The parts increase in difficulty. But I do have 3 parts. I do need to write everything out. And what have we got? Let k be a positive integer greater than or equal to 2. 2 bags each contain k balls labeled with the positive integers from 1 to k. Andre removes 1 ball from each bag. In each bag, each ball is equally likely to be chosen. Okay, so no weird probability surprises here. Define P of k to be the probability that the product of the numbers on the 2 balls that he chooses is divisible by k. Okay. So this probability will sort of scale depending on what k is. Now, Andre doesn't have to be choosing factors. They just need to multiply to be some sort of multiple of k. Okay. So it looks like 10 is entirely based around this pk thing, so I'm actually going to read every part all at once. It might give me some direction as to where to go. So A, calculate p of 10. This should be a couple easy marks just to see, do we understand what it is they've just described. B, determine with justification a polynomial fn for which pn is always greater than or equal to fn over n squared. Now the n squared here is because I don't know why they switched it from k to n, but whatever. You're always going to have k times k many balls to be, or many pairs of balls to be picked. So all of the probabilities can be measured out of k squared, or I guess n squared. So Pn is greater than or equal to Fn over n squared for all positive integers n, greater than or equal to 2. Otherwise, I don't think we'd be defining this. And we also need P of n is equal to Fn over n squared for infinitely many positive integers. So maybe for some reason Fn, maybe you always have, so I'm just trying to think of an infinite family we might use. So maybe, for example, P of 2 to the m is always equal to Fm, or F2 to the m over 2 to the m squared. Maybe there's something like that, in which case, there's an infinite number of powers of 2, and it might not be powers of 2, it might just be powers of primes. I have no idea. Prime numbers, it could just be prime numbers, who knows? But we start thinking about an infinite number of possibilities. So this is sort of the bare minimum, and what they're saying here is the minimum is always achieved. In fact, it's achieved infinitely often. Okay. So when we do A, we might want to carefully try and figure out, alright, how are we calculating P of 10? And that might influence the Fn that we work with. Okay, and then C part here. Prove there exists a positive integer m for which Pm is greater than 2016 over m. This is different than over m squared, so this would, it's got to be great. This would be equal to 2016 m over m squared. So, can I ensure that fm is, I guess, less than 2016 m for some sufficiently large value of m or something like that? I'm not entirely sure where to go with that. Okay, well, let's start off easy. We'll just calculate A. So, in order to calculate P of 10, what are we doing? We've got sort of a bag over here, and it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we've got a second bag over here. With the same number. So one thing I'm going to just sort of note, and they've sort of implicitly noted this already in their probabilities, for any k, there are k squared ways to pick one ball from each bag. So I'm just saying pk is always something out of k squared. That's what I'm trying to get at here. Okay? So, you know, it is a written question. We do need to justify what it is that we're talking about. Alright, so Andre comes along and say he picks out 4 from this bag. So he's got a 4, that's his first one. What could he have? Because now, if we want to figure out the top number, we sort of need to calculate how many ways the conditions of the question can be satisfied. So, if I've got 4 there, I need to pick something that would give me a multiple of 10. Well, 4 has a factor of 2 in it, so to make 10, I need a 2 and I need a 5. 4 has a factor of 2. It's got a couple factors of 2, but we just need 1. So I guess I need things that have factors of 5. So 4, 5. 4, 10, that should be about it. I guess we could brute force an answer just by saying, alright, so we'll say we're doing casework. If I pick a 1, well, that has no factors that contribute to the 10, so I have to pick out 10 here. Because you need the 2 and the 5 at least, and that makes 10. But if I pick 2 first, well, there's a factor of 2, so I could just get away with having a factor of 5, and that can come from either a 5 or a 10. If I pick a 3, 3 contributes no factors to my product of 10. Remember, to have a product of 10, we need a 2 and a 5, so you're stuck with that. In fact, 7 should also work that way, and 9 also will do that, because 9 and 7 don't bring any factors. They have no factors in common with 10. Interesting. 4, I've already said, does 4, 5, and 4, 10. And the same thing should work with 6. 6 just brings a factor of 2 to the table. So 6, 5, 6, 10. And similarly with 8. It's got lots of factors of 2, but we just need the 1. And then, well, 10 goes with everything. Right? As if Andre picks the 10 out, there is a 10, right? It's 1 up to k. Yeah. 1 up to k. So if Andre picks the 10 out, it doesn't really matter what the second one he picks is. Just like for all of these, you're going to have 10 as the second number, and that'll always work out. 10, 9. I guess we can squeeze in 10, 10 just in the corner there. And then 5. So 5 brings a factor of 5 there. I still need a factor of 2, so we have 5, 2, 5, 4, 5, 6, 5, 8, and of course 5, 10 as always. So this would be what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 2, 3, 4, 5, 6, 27. Okay? And it's okay to just have my answer brute forced like this. That gets me my answer. That's okay. So P10 should be 27 out of the 10 squared, or 27 out of the 100 ways to pick pairs of balls. We'll have the product of those two numbers be a multiple of 10, be divisible by 10. But are there patterns here I can see? Or are there things that would suggest a pattern, and maybe looking at something else like 8 or 12 or 11 might help me with? So when I chose a 1, there was only one number, and that also happened with 3 and 7 and 9. So I'm going to highlight these as these ones only gave me 1. And then with 2, there were 2 of them. And 4, there were 2 of them. And 6, there were 2 of them. And 8, there were 2 of them. And with 5 gave me, if 5 is the first term, you got 5 of them. And if 10 is the first term, I got 10 of them. 1s, 2s, 5s, and 10s, these are the factors of 10. So it looks like, here's an observation. If Andre picks A out of the first bag. Then looks like there are GCD of A and K. Possible balls to pick from the second bag. That seems to be an observation borne out by these numbers. The fact that we got 2s and 5s. And 5 here occurs because, well, the first number is 5, and 5 GCD with 10. The greatest common divisor of 5 and 10 is just 5. Greatest common divisor of 4 and 10 is just 2. It works that way with all the even numbers. Now, it might not be GCDs. I want to justify this. I could be missing something, because it's not like 10 is 20, where maybe 4 could give us more possibilities. Because 10 is just a product of 2 primes. It might just be the lowest square-free number that divides the GCD. I'm not entirely sure. Or the biggest square-free number that divides the GCD. I'm not entirely sure here. So, I'm pretty sure this is true, but why would this be true? So let's prove this. Indeed. Let's just give a name to the GCD. Then if B is the second ball picked, and K divides A times B, then, so if I let A be D times whatever's left over, and K be D times whatever's left over, and since K divides, I'll let KC be AB, so then dk prime C is equal to dA prime B. Divide by D's here. K prime and A prime have nothing in common. So K prime must divide B. Okay. So I'm using sort of relatively prime property. So I know that whatever's left when I divide K by D must divide this other number. How many B are there? Which have K over D as a factor. Well, there's K numbers, and so we just go up by multiples of K by D, and that resolves to D, which happen to be the GCD of A and K. So that's sort of my proof. It could probably be written out a little bit better. You know, for example, you would say like this. I'm just trying to write it up a little nicer and neater. Since K divides AB, there is C, so that KC is equal to AB. So K prime divides A prime B, and therefore K prime divides B, since the GCD of A prime K prime is equal to 1. There we go. Since they're relatively prime, it has no factors in common with A prime, so all of the factors of K prime in this product are hidden in B. Okay. So this is great. So I've proved the result. So number of ways to pick a pair. I don't want to keep saying this. I'm going to call this having Andre's condition. I'm going to let this be A of n. Is the sum of all let's write it this way. The GCD of 1 with n. Well, I've been using k, haven't I? It's sort of a GCD sum function. All the way up to kk. So that's what's equal to this ak. And then p of k is a of k over k squared. Now, I don't think ak is a polynomial. Otherwise, I feel like in B they would just ask us for that polynomial. But maybe there's a way to show that ak is always greater than some polynomial in terms of k. So I've definitely moved past A part, where we got the answer of 27 over 100. And now we're into B part. We're exploring the number of ways to pick a pair of balls and have their product be a multiple of k. So I've got an expression for that. Good. And now it's time to start thinking about, well, what could Fn be? And, what could be the infinitely many positive integers? So because we're talking about GCDs here, GCDs can be fairly unpredictable depending on what k is. I mean, if k is something like a whole bunch of products of primes to various powers, you're going to have a heck of a time trying to keep track of all this. But if we keep k simple, like powers of primes or just primes, the GCD story, especially if, so let's say let k be p a prime. For any L less than k, but greater than or equal to 1, well, actually we can call it p, the GCD of L and P is equal to 1 because, well, primes don't have any number in common with them other than themselves. They don't have any factors to share with anything that's less than them. And then, so there are P minus 1 many L. And then for L equal to P, the GCD of L and P, well, it's the GCD of P with itself. Anything with itself is just P. So I think what we've shown here is for a prime P, A of P is P minus 1 times 1 plus 1 times P, and that's going to be 2P minus 1. So that's good. So I wonder if, so I'm going to let Fn be 2n minus 1. And we see for any prime P, P of P is AP over P squared, but we just said that that's 2P minus 1 over P squared, which is FP over P squared. So that would give me my infinite family. So that would satisfy this condition down here, but I also need to show that every n, for all positive integers n, P of n is greater than or equal to 2n minus 1 over n squared. That, I think, will be a little harder. So we'll say something like, it suffices now to show an is greater than or equal to 2n minus 1 for all n. So, first thing I'm going to say is notice that the GCD of n and n is always n. You can't really escape that. And for any L less than n, well, GCDs are always greater than or equal to 1, right? So A of n is GCD of 1 and n plus GCD of 2 and n plus, we'll write in another one, GCD of 3 and n, GCD of n minus 1 and n, GCD of n and n. But this is greater than or equal to 1. This one's greater than or equal to 1. Greater than or equal to 1. And this is always equal to n. GCD of n with itself is equal to n, as we said above. Now there are n minus 1 numbers that are less than n. So 2n minus 1, and that's my f of n. So, I think we've got it. So p of n is, by my definition, with what I'm calling Andre's condition. Andre's condition, we could probably define that in our notes if we wanted to keep saying it. But it's just that two balls are picked and their product is divisible by n or k or whatever you want to call it. But since an is greater than or equal to fn by our previous proof, we have that other condition, and that shows b. So that's done, that's done. And now we can attempt c here, I guess. Prove there exists a positive integer n for which pm, so a positive integer m for which pm is greater than 2016 over m. So for a moment I was tempted to use my formula and try and make 2p minus 1 over p squared. Problem with that is, one, we don't just have a p down here. Second, they specifically want greater, and I showed a moment ago that this is equal for primes. So we actually have to be greater than. So what can we do? There might be a closed form for an out there, but it's not going to be nice because, again, I feel like if an could be a polynomial, they would have just asked us for that polynomial and saying, instead, let's just get a polynomial fn that's always less than or equal to it. So I think a closed form for an isn't going to work. I think we need to look for a special case. Primes aren't going to cut it. But again, as I said, if n or k or whatever you want to call it is really wild and crazy, you're not going to be able to really get a handle on all those GCDs. So, I mean, there's a couple approaches. We could try n being just a nice simple product of two primes. That could be good, two different primes. That would probably allow us some escape. Or we might say, well, let's just let it be a power of a single prime. Or not a, I think we've used a already. Let's say e. Those I think are the two most basic options to try. I can't say for certain which one I think might necessarily be better. Try either one. Try PQ. Well, we'll try PQ for a little while, and if that doesn't work, maybe I'll try powers of prime, and if that doesn't work, I will really go back to the drawing board. Alright, so... Oh, and we have an example in 10 that's P times Q. So maybe that's a good idea. Maybe that's us being on the right track. Okay, so if N is equal to PQ and L is somewhere between P and Q, well, if N is equal to L, the GCD, we've already said, that's going to have to be N, which in this case is PQ. If P divides L, but Q doesn't divide L, the GCD of Ln is going to be, well, just P. And how many of those are there? Well, there's N over P, which is Q of them, that are multiples of P, but one of those is N itself, which is also a multiple of Q. So there's Q many of these. Similarly, if we let Q be the only factor of L, there's going to be P minus 1 many of those that have the GCD of L and N be equal to Q. And then the rest have P not divide L and Q not divide L. So the GCD is 1. So I think we can get a formula here. There's going to be 1 that's a multiple of N. I'll just write that. One where the GCD is N. There's going to be P minus 1 of them where the GCD is Q. There's going to be Q minus 1 of them where the GCD is P. And then the remaining ones, so N minus this one, minus these P minus 1s, and minus these Q minus 1s, times 1. So we can simplify this a little bit. PQ minus Q, PQ minus P, PQ minus 1 minus P minus 1 minus Q minus 1 is plus 1. Okay. This minus 1 and this plus 1 cancel out. Good. There's 4 PQs. 1, 2, 3, 4. Minus 2 P's minus 2 Q's. Plus 1, 1. I feel like there's a formula for this. Oh, that's cool. So with just a single prime, AP is 2P minus 1. If I've got 2 primes, it's a product. I think A might be what's called a multiplicative function, that if you got A of xy and xy have no factors in common, then you get that. This is what's known as a multiplicative function. I don't know if this is true. I might have to prove this to answer the question. I'm not sure. But, well, let's see what we can see then. So there's my formula for APQ. So what would that do? So we'd get APQ over PQ squared. That would be 2P minus 1, 2Q minus 1 over P squared Q squared. And I want that to be greater than 2016 over PQ. So I suppose we can multiply both sides by P squared Q squared. But actually, if we expand this back out, we're going to have a horrible time. This is not going to work. So while we were able to get a formula for APQ, which is nice and hints at something perhaps a bit grander, this is always going to be positive in a very, very big thing, and this is always going to be negative. So, okay, that didn't work. And I don't think adding on extra factors of extra single primes is going to help us in any way either. So, I mean, it might, but I don't think it will. So maybe try the other method. Maybe try a power of a prime. Maybe get a formula that way. And then if I'm right and it's multiplicative, that would actually be able to sort of try and give us a formula for an, or a method to figure out an for any n. I would also explain why an is not a polynomial, because it depends on the factorization of n, which can't be expressed with polynomials. But, okay. So, if I'm just dealing with a power of a prime, well, maybe let's do it with square first, just to make our lives a little easier. And then, because maybe I don't have to generalize that hard. But, okay. So, if I think about numbers, so what are the possible GCDs? You could either have a GCD of p squared, but then L has to be p squared, and that's only going to happen once. Or we could have, well, the GCD has to be a factor of p squared, so it could be p. But that means p divides L, but p squared does not divide L. Just like up here, it forced p squared to divide L, and that sort of forced L to be equal to p squared. So how many of those are there? Well, there's p squared numbers to consider. P of them are going to be multiples of p, but one of them is a multiple of p squared. So just like before, there are p minus 1 many that do this. Or you could have just 1, in which case 1 divides L, obviously, but p does not divide L, and that's just going to be the remaining p squared. There are p squared of them, minus 1, minus p minus 1, p squared minus p of these. So, we should get 1 times p squared, p minus 1 times p, and then p squared minus p of them times, and each of those is equal to 1. So that's p squared minus p, p squared minus p, 3 p squareds minus 2 p's. Okay. So, well, I mean, we're here, we could try it. Maybe I don't have to go p to some ridiculously high power. I feel like I might, though. So we'd have 3p squared minus 2p's, p to the 4, 2016, p squared multiplied by p to the 4 on both sides. So we'll get 3p squared minus 2p has to be greater than 2016 p squared. So minus 2p has to be greater than 2013 p squared. Again, this is not... I mean, we can divide by p on both sides, certainly. But this isn't going well. Well, maybe we do need to shoot higher. Now, when I just had p to the 1, it was 2p to the 1 minus 1, which is technically p to the 0. And with p squared, I had 3p squared minus 2p to the 1. My guess would be ap cubed is going to be 4p cubed minus 3p squared. That's my guess, and so more generally, I think we could get a nice form for a p to any power. Now, in terms of the GCDs, you could have p to the e. There's only going to be one of those. or it could be p to the e minus 1. How many L's are there going to be that do that? So p to the e minus 1 has to divide L, but p to the e cannot divide L. So there'll be p minus 1 of those. Or it could be p to the e minus 2. And so you'll need p to the e, you'll need it to be a multiple of p to the e minus 2, but it can't be any of the p multiples of p to the e minus 1. Yes, okay, so in general, we get p to the f occurs for, what is it, p to the e minus f minus p to the e minus f minus 1 many values of L. Okay, so a of p to the e should be 1 GCD that's p to the e, p minus 1 of them that's p to the e minus 1, p squared minus p of them that should be p to the e minus 2, p cubed minus p squared of them that are p to the e minus 3, then all the way down to p to the e minus 1, where the GCD is just 1. Does that track with what we saw before? Yes. Okay, and it tracks it, so that would be a GCD of p to the 0. So yes, okay, it all works with our formula. So it's going to be 1p to the e, and then a bunch of these are going to be, so the p here and the p to the e minus 1 give me a p to the e. The p squared and the p to the e minus 2 combine to give me a p to the e. And then once again, we're sort of left hanging with one factor omitted. So this is going to be a single p to the e, and then so that's so p to the 0, 1, 2, 3, all the way up to e minus 1. How many numbers between 0 and e minus 1 inclusive? E of them. So there's e p to the e's coming from here and 1 from here. E plus 1, p to the e, minus e p to the e minus 1. Okay. So that works, and if my earlier comment about a being multiplicative is true, which you might want to prove on your own, I think there's sort of a general way to now figure out all a to the n's, but this might be enough. So we'll say p of p to the e is a p to the e over p to the e squared, and this is equal to e plus 1 p to the e minus e p to the e minus 1 over p to the 2e, and I want this to be greater than 2016 p to the e. Multiply both sides by p to the 2e. And I'll have to have greater than 2016 p to the e. But as long as I choose, I was going to say choose e to be 2016, but that we're subtracting over here. So what can we do? Oh, I can divide by p to the e minus 1, right? And so minus e has to be less than p times 2016 minus 1 minus E. So if E is big enough, this side can actually be negative and might be less than this. Well, we don't have to be fancy about this. I don't see a nicer way to deal with this formula here. Actually, you know what? We could regroup it a different way. No, I don't... I want to try and get these P's together. So E minus 2015 times P has to be greater than E. So P has to be greater than E over E minus 2015. So if I do something like let E be 2016, we'd have 2016 over 2016 minus 2015, and that's 2016, and I just need a P that's greater than that, so any prime greater than 2016 will do, so just find one. I don't know, maybe 2017 will work. I'm just going to grab my calculator. But there's got to be some prime that'll work. 2017, what's the square root of 2017? It's about 45, right? So, it's not a multiple of 7. Not a multiple of 11. 13, no. How about 17? Certainly not. Divided by 19, nope, 2017 is not a multiple of 19. 23, nope. 29, no. How about 31? Nope. 37, no. 41 would be the next prime to try, nope. 43, no, so 2017 is prime and greater than 2016. So, I think it should work. So, P of 2017 to the 2016 should be equal to 2017 to the 2016. I'll do this on the next page, actually. Just want to double check, make sure all my work works out. So that's going to be 2017. Add 1 to the power up here. And then 2016 times 2 to the 2017 to the 2015. 1 less, all over 2017 to the 4032, and then what can we do? So that's 2017 to the 2017 minus 2016 let's divide by 2017 to the 2017 to the 2015 on top and bottom. So I'll be left with 2 of those there, minus a 2016 here. 4032 minus 2015 would be 2017 to the 2017. And then, is this greater than 2016 up here? So if I multiply both sides, by 2017 to the 2017, add 2016 to both sides, I'll get 2017 squared is greater than 2016 times 2018, because I've added one 2016. And that is true because this is actually equal to 2017 squared minus 1. So that does work. I'm sure it's not the only one. I sort of chose an E value here. 2017 might not be the lowest prime that does this. But we've got one that works, which is nice. What else could we do? Could I find a way to make 2 work? So I like this equation here, E minus 2015. That's really what we need to have satisfied. As long as you have that, P of P to the E will always be what we want. So I'll just say let M be 2017 to the 2016. But what if instead I said I want my prime to be 2? Then I need 2E minus 4030 to be greater than E. So I need E minus 4030 to be greater than 0. So 2E to the 4031 should also work, if our math is correct. Let's check that, just because we can. I mean, I admit I finished the question, but I'm just intrigued by this. I like powers of primes. So that's going to be add 1 to the the exponent. Subtract 1 there. 2 to the 8062. So, well, we can simplify this side a lot to divide by 4030. And that'll be 2 to the 4032. So if I multiply through, I'll get an extra 2 here. And so 4 times 2016 minus, should be 4033 on this side, and this is 4032 on this side. So, yeah, that one also works. Kind of cool. And I think just to close the video off, just because it's been kind of intriguing, I just want to say more generally, if n is that P1 to the E1 stuff that I've been fearing, I'm fairly certain that you just need to multiply all of these out. E1 plus 1, because it's multiplicative. I'm pretty sure we didn't show it, but I'm pretty sure you can show it. But certainly using this expression would have been a nightmare to try and answer the question. So stumbling upon powers of primes really was the right way to go. Although maybe if we had added enough single primes, it could have worked out. I didn't spend too long exploring that, but it's possible. Absolutely possible, but there we go. There's sort of your general formula for an in terms of the prime factorization of n. And we're done. In fact, I answered this last one twice. 2 to the 4031 or 2017 to the 2016. Both of those are fine answers. And you can actually use that formula. What was it? P greater than E over E minus 2015 to find really any of them. I think that should completely characterize all m's being equal to powers of primes that do this. But I have gone on for a little too long. I think we're going to close things off there. It's been a very interesting 2016 paper. And if you're interested in more Euclids, if you want to practice because the Euclid's coming up, then by all means, you can take a look on my channel. I've got many, many more Euclids for you to take a look at. So, happy hunting, and I'll see you for more math in the future.